The next lesson in section 2.4 has us finding more zeros of polynomial functions. This time we're going to find both real zeros and complex zeros of polynomial functions. So the search is on for where the polynomials are going to cross the x-axis, the x-intercepts, which are also called the zeros of the function or the solution. So really in the whole scheme of things, what we're trying to do is we're trying to learn some methods to solve polynomial functions. So that's what we're going to be discussing. The first one is, how do we find real zeros? And they're going to give us some indicators and pointers on how to find them and search clues to find these real zeros. So first of all, they want us to recall that a polynomial function of degree n can have at most n real zeros. So those are just possibilities. Remember, if it was a third degree polynomial, it could have at most 3, 2, or 1 real zeros. But an odd function always had 1 real zero. Where if it was an even function, say it was x to the fourth, it could have as many as 4, 3, 2, 1, or as few as 0 zeros. So we're trying to find those real zeros. There are two different types of real zeros. One is called rational zeros. Now rationals are just numbers that can be written as a ratio of two integers, such as 2/3. That's a rational zero. Or simply an integer like a -3, or another one could be a +3, or any integer, any rational number like a fraction. There are also some irrational zeros that we will be finding, and these are in the form that you see with the equation for gx, where we had x squared equals 5. If we solve that for x, we would find that x would equal plus or minus 5, square root of 5. So any radical that doesn't come out as a perfect square will be our irrational number. Another way to describe irrational numbers is that they are either they don't repeat, nor do they terminate as far as decimal approximations. So they'll light up your entire calculator, and all they'll do is approximate them. But one of the things they give us to try to help us find the rational zeros is a rational zero theorem. And it describes how we can use the leading coefficient and the constant term of a polynomial function to determine a list of all possible rational zeros. So what's different about today's lesson is, if you notice just in the example here, what they're going to give you is simply a polynomial function, and that's all that you get. They don't tell you to test, is this a zero? We have to come up with this list on our own. And the rational zero theorem is there to help us narrow down this search for the intersections. Now, this was a lot more valuable of a concept before we ever introduced the technology of graphing calculators or whatever program you're using on your calculator. So keep in mind there's kind of an evolution of what's been going on mathematically once technology has been available, how we're going to present this and teach it to students in any math course. So this rational zero theorem is a good theorem. It does help us find the number of possibilities, but we are also going to rely very heavily on our graphing calculator to help us find the location of these. It doesn't allow us to dismiss the skill of synthetic division, because we're still going to need that to find some of these irrational and also the complex solutions. So keep in mind, we're going to be using these graphs. Don't think that you can cheat the system by relying entirely on graphs, because we will eventually need to learn this whole method to complete the system of operations that we're going to be doing. So anyhow, the rational zero theorem is stated there in that box. I will rephrase that down here as I work through question number 1A and 1B. Question 1A and 1B, they want us to use the rational zero theorem to help us find all possible solutions. And I have to reorient the board because it's not quite hitting the right spot. So I'm going to pause this and we're going to start it again here. Alright, the board's reoriented, so hopefully it'll track a little bit better. I can minimize that and we'll start again. List all possible rational zeros of each function. That means we're going to be using this rational zero theorem. So according to the rational zero theorem, what you can read about up there is, if this is a polynomial function as we have in question A, and the constant isn't 0, and all of these powers, in order to be a polynomial function, have to be integer powers, we can use this theorem. It's called the rational zero theorem. I'll go rational zero theorem, and it basically states, go and find your constant, which is a -2, which the sign isn't that imperative, but write all the factors of your constant term on the top, and then the other thing you want to go retrieve is you want to retrieve the leading coefficient. So in the leading coefficient, you want to write down all the factors of the leading coefficient. So I'll go LC for leading coefficient. So here's what we're doing. We're up here, we see that the constant is 2. What are the possible factors of 2? Well, they are 1 and 2. But when we do this, we always want to consider a plus and a minus on those. So we'll always list plus or minus 1 times 2. Divided by, now we'll go to our factors of our leading coefficient. Our leading coefficient is 1, so the only factors of 1 are 1, so it's plus or minus 1. Now, leading coefficient, or the rational zero theorem says, if you write the ratio of all of these possibilities, which would really be taking a plus or minus 1 divided by a plus or minus 1, and then a plus or minus 2 all over a plus or minus 1, well, our list is pretty small on this one. Our list just becomes, if you take a positive 1 divided by a positive 1, it's just a 1. If you take a positive 1 divided by a negative 1, it's a negative 1. In any combination of that, all it's going to give you is a plus or minus 1. The same thing on the positive 2 divided by a positive 1 will give you a 2. A negative 2 divided by a positive 1 would give you a negative 2. And then if you started doing the opposite, taking a positive 2 divided by a negative, it'd still be a negative 2. Negative 2 divided by a negative would give you a positive 2. So realistically, whenever you get just a plus or minus 1 there, your list is going to be comprised of just your constant factors. So you're going to see that, and that's what the heading is on this one. We have a leading coefficient that's equal to 1. In the next example, you'll see, at least in examples 2, you'll see where that leading coefficient is something other than 1, and it makes our possibilities much larger. Now, like I said, we're not going to turn a blind eye to technology. We are going to use that to our advantage here, along with synthetic division. So we just did the rational zero theorem. I still think I'll have you remember what the rational zero theorem says and how to find the possibles. And this is what you would list. It would be plus or minus 1 or plus or minus 2 are your possible factors of this polynomial. Okay, so once we have our list, what I'm going to do is I'm going to go and I'm going to look at the graph that I've done. And I've positioned the graph here in front of us. And I'm looking at where this graph is crossing the axes. So there's one crossing there, there's another crossing here, another crossing there. Of all those crossings, which one of those matches up best with the list that I have? Is there a rational zero? And the best that I can do is I could say, well, it looks like maybe it's crossing here at a positive 1. So we're going to use our synthetic division. And I kind of set up a little bit of a synthetic division bar here. So I'm going to get some room on that. We're going to divide it by a positive 1. I think that's where it's crossing right there. We're going to put in our numbers, which are 1, 5, negative 4, and a negative 2. To do our synthetic division, I'm going to introduce a little bit of a change to it. I'm going to, instead of writing all the calculations down, we're going to do a little shorthand version. Most of this we can do in our head. So first thing we do is bring down our 1. I go 1 times 1 is 1, add it to 5, which is 6. 1 times 6 is 6, add it to a negative 4, which is 2. 1 times 2 is 2, add it to a negative 2 is 0. And as we suspected from our graph, this is actually a 0 of the function. We can tell because our remainder is 0 as well. So it was a third-degree polynomial starting up in our first line, and now we got it down to a second-degree polynomial in our second line. As soon as you get to a second-degree polynomial, I would rewrite it as x squared plus 6x plus 2. And we're trying to see if this thing will factor again. If we look at our graph, it doesn't appear that these are going to be anything easy to find. So if we are going to try to factor it, it's probably not going to be anything real kind to us. And as you can see, the factors of x squared are x and x. The only factors of 2 are 2 and 1. And there's no way a plus 1 and a plus 2 will give you a 6x. So this does not factor into nice, neat factors that way. The only other way that we could possibly try to find those factors would be to use our quadratic formula. So we have x squared plus 6x plus 2. Now in this, what we'll do is we'll take the opposite of b, so negative 6 plus or minus the square root of 6 squared minus 4 times a times c all over 2 times a, which is 2. So it's a negative 6 plus or minus the square root of 36 minus, then we have 4 times 2, which is 8, all over 2. Extend the page. That means you have a negative 6 plus or minus the square root of, and a 36 minus 8 should be a 28, all over 2. Simplifying, it's a negative 6 plus or minus Just thinking out loud here, we got 28. The perfect square of 28 is 4 times 7. So taking the perfect square out, it's 2 times the square root of 7. So it's plus or minus 2 times the square root of 7 all over 2. And then we can find our final solutions then by taking a negative 6 divided by 2 plus or minus 2 square roots of 7 divided by 2. And we can see that it's a negative 3 plus or minus the square root of 7. Now these are going to be the representations that we have on our graph for this location right here and this location right there. And if we took our calculators and we did the decimal approximations of them, that should seem reasonable. Okay, so we're supposed to make a list of all rational zeros of each function and determine which of any are zeros. So here's what I've done with this thing. I've gone farther than we needed to go just to show you the whole process of how we're going to find all the zeros. So all they want us to do in the directions on this one is to get to this level. Once we got to the level of it being a quadratic, take a look at this quadratic. Will it factor into any decent rational factors? And we looked at that earlier, and there was nothing that we're going to be able to do with the 2 and a 1 to get a 6. Just to kind of reemphasize, the only integer factors of 2 are 2 and 1, and there's no way we're going to get a 6. So that was a red flag to me saying the other roots are not going to be rational. And as you can see, these roots down here are not rational, they're irrational because the square root of 7 is an irrational number. Okay, so I tried to give you a little bit more of a whole scheme picture of what's going on here inside of the context of this problem. Okay, so the next one I'll stick more to just the facts here and what they want us to do on this problem. So, clearing the board off here, at least attempting to, we're going to start the next problem. Next problem, we're going to use the rational zero theorem to figure out how many possible rational zeros there are. So, using our rational zero theorem, I need the constant factors over the leading coefficient factors. Now the constant in this one is 30, so it has a lot of possibilities. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4 doesn't work, but 5 does, then plus or minus 6. Now we're on the other side, it's 3 times 10, and now it's 2 times 15, and it's going to be 1 times plus or minus 30. Those are all of the factors of the constant. Now I take it over the leading coefficient. Well, our leading coefficient in this problem is 1, so it's just over plus or minus 1. So if I divide all these numbers by plus or minus 1, it doesn't change it. So really our list of possibilities are this, or is this list that I just circled in green. So these are our possibilities for being a rational zero. So I don't want to lose track of those, so I'm going to move them to a different location here for a second and kind of keep them on the back burner because I'm going to test them. So that we're not shooting in the dark, and this is where I said we're going to kind of merge some of our ideas with what technology can afford us. We can come up to the graph that I have shown here in red, and it looks like one of the possible crossings would be at a negative 4. But as you can see, that negative 4 is not showing up on our graph here, or on our possibilities. So we're going to have to do a little creative searching for this one. Okay, I took a little pause on that because when I looked at my graph, the graph didn't look quite right because it didn't seem like it had the right features of the graph that I needed. So what I did is I went back and I regraphed it, and this is actually the graph of that equation. So it gives us a little bit better picture of what's going on because it's the actual graph. So now coming back to my list here, here's what I wanted to show and what I wanted to be able to do with it. I can see that our graph from our graphing calculator says it should be crossing at 2. So I'm going to try 2 as a zero the function into our polynomial, which if we take out its constants are 1, 3, negative 7, 9, negative 30. And I'm going to test and see if 2 goes into it evenly. So we're going to use our synthetic division. Bring down the 1. 2 times 1 is 2. Add it to 3, which is a 5. 2 times 5 is 10. 10 added to a negative 7 is 3. 2 times 3 is 6. 6 onto 9 is 15. Then 2 times 15 is 30. 30 onto a negative 30 is 0. So there it is. There's the confirmation that 2 is actually a zero of the function, which means if we wanted to go that far, we could say that x minus 2 is a factor. So it started out as a 4th-degree polynomial. Now it's going to be whittled down to a 3rd-degree polynomial. But we really don't have any great methods of finding the factorization of a 3rd-degree polynomial. So what we're going to do is we're going to bring in another piece of our synthetic division chart. And now I'm going to look at my graph again and see what is another possibility. Another possibility looks like that could be crossing through at, I'm going to try that -5. Put the -5 in and see how this works. So now I'm going to run through this row. I'll use a black marker and we'll bring down our 1. And I'm going to use this depressed row here. I don't need the 0, but if I use this depressed row, then I don't have to do as much synthetic division. It'll give me the same results. So I need to see if -5 will go into our cubic function that we have factored. So -5 times 1 is a -5. -5 plus 5 is 0. -5 times 0 is 0. 0 added on to 3 is 3. -5 times 3 is a -15, and -15 plus 15 is 0. So here it is. There's our confirmation that -5 is also a zeroth function, just as our graph is suggesting. What we have left now is a quadratic equation, which is a 2nd degree. So we've got an x squared plus 0x, so I don't need to write that, plus 3. If you set that equal to 0 and you think, can I factor that, or can I find the values of x that make this true, and are they rational? Well, that means x would equal, or x squared would equal a -3. Right away, we should see a red flag, because now we're taking the square root of a negative. Now we've done this, but it's the square root of 3i, and it's plus or minus. I'm sorry, I forgot to put that in there. Whenever you square roots, plus or minus. But the problem with this is it's not real. So this is a non-real solution, and all we're after are the rationals. So the only 2 rational zeros of this function are 2 and a -5. So 2 and a -5 are the only rational zeros. The others are going to be complex solutions, and we're going to disregard those for right now because our directions don't ask us to find those. So there are 2 different models of using the rational zero theorem, along with our technology and graphing features to find the real zeros and decompress the equation to smaller and smaller degrees.